Hello once again everybody, thank you for joining me in this video where it's a third in chapter 2 on Edexcel's year 13 maths course looking at functions. So in 2.1 we had a look at the modulus function, 2.2 we introduced the concepts of domain, range and mappings, and here we're going to go back into GCSE and add a bit more to our current understanding of composite functions where we compose, for example, multiple functions together. So before we get stuck into that though, I want you to have a go at these 4 warm-up questions for me. So pause the video now and try these independently. When you've done and think you've got the best solutions you can, press play and check your answers against mine, and hopefully they should match. And if not, hopefully this video should help in terms of seeing why they don't match. Okay, assuming you've done that, let's have a look together at warm-up question 1. So question 1, we have 2 functions, f and x, defined as follows. F of x is 2x plus 1, and g of x is just simply x squared. So find, first of all, f of 2. So f of 2 means our input into this f function is simply 2. So instead of x, we're using the exact specific 2. So f of 2 will simply be 2 lots of 2 plus 1. We get the 2 because the input now isn't just a simple x, it's a specific 2. 2 times 2 is 4, plus 1 gives us 5. Next, we want to work out g of 5. So g of x takes the input and squares it. So if our specific input is 5, that's going to be 5 squared, which gives 25, because the input, of course, was our 5. G of 2 means our input now is 2, so instead of doing 5 squared as before, this time we're going to do 2 squared. So G of 2 is the same as 2 squared, which of course is 4. Finally, f of 4 means we're going to do 2 lots of 4 plus 1, because our input this time is the specific 4, not just the x. So 2x plus 1 becomes 2 lots of 4 plus 1. 2 lots of 4 is 8, plus 1 is 9. Hopefully you did question 1 without too much trouble at all. If so, I hope that's just helped you to get away some of the rust. Let's have a look at warm-up question 2. Question 2, just some simple expanding and simplifying. So first of all, 3 times 3x is 9x. 3 times minus 2 is minus 6, and finally minus another 2, overall gives us 9x subtract 8. The next one, we need to square this out and then minus 1. So this one, slightly more complicated, but nothing that should trouble us too much if we take care. 3x all squared is 9x squared. We take the product and double, so 3x multiplied by minus 2 is minus 6, double minus 6 to give us minus 12x's. Minus 2 times minus 2 is plus 4, then of course minus the 1. And so this bracket all squared just gives us this bit, which can then simplify down to give our final answer. So we have 9x squared minus 12x and plus 4 minus 1 overall is positive 3. And the last one, 3 lots of x squared minus 1 minus 2 is 3 lots of, what am I doing here? Being silly is what I'm doing. So 3 times x squared, of course, is 3x squared. 3 times minus 1 is minus 3. Then minus the 2 on the outside simplifies to give us 3x squared minus 5 overall. Question 3, we have a function given as f of x takes the input and maps it to 1 over the input plus 1. Where x is defined as being greater than 0. So we need to deduce the range of f. So if we just sketch out a graph here and make a note that we want x to be greater than 0. So f of 0, let's just think what that would be. F of 0 would be 1 over 0 plus 1, which is 1 over 1, which would be 1. And so if 0 were allowed, which it's not, f of 0 would be 1. So I'm going to put here a hollow circle at the height of 1. That's for f of x. This is for x. And then obviously as x goes bigger and bigger and bigger, it will become 1 over 100, 1 over 1,000th, 1 over a millionth, and so on and so on. So this graph will get smaller and smaller and smaller, but will never actually quite touch the x-axis. It will never quite touch. And so the range of this function is that f of x is no greater than 1. In fact, it can't be 1 because x has to be greater than 0. So it has to be smaller than 1, but of course it has to be greater than 0. So the range of our function is as follows. And finally, warm-up question 4. Here we have to simplify fully this awkward fraction within a fraction. So we've got on the top of the fraction this x plus 2 over x minus 4 plus 1, all divided by this weird denominator, which is a combination of a fraction and then this minus 1. So my suggestion for the best first decision to get this cleared up will be to multiply both the top and bottom, the whole of the yellow and the whole of the green, by this denominator hidden inside the fraction itself, x minus 4. So if I multiply the top by x minus 4 and the denominator by x minus 4, this will help us to get it neatened up slightly. So this part here, x plus 2 divided by x minus 4 times x minus 4, will just leave us with the x plus 2 left. Then we'll have 1 multiplied by the x minus 4. And on the bottom, x plus 2 divided by x minus 4 multiply x minus 4 will cancel, just leaving us again the x plus 2. And then we'll have minus 1, lots of x minus 4. So now we can expand these brackets quite simply and then simplify even further. So the top, we're going to have x plus 2 plus another x. 1 times minus 4 is minus 4, all over x plus 2 minus 1 times x is minus 1x. Minus 1 multiplied by minus 4 is positive 4. So simplifying this further, on the top we have 2x minus 2. And on the bottom, x minus x cancels, and 2 plus 4 is 6. And finally this simplifies down because all terms are even, so dividing through by 2, finally we have x minus 1 all over 3. So now that we're suitably warmed up, let's have a look at the main part of today's lesson. Composite functions. So we're going to dive back into GCSE and add a bit more rigour to it. So composite functions, what do we mean by this? Well, hopefully this will make some sense and will jog your memory. So it's essentially when we combine two or more functions to make a new one from it. So the new function is called a composite function. So here's a little diagram that illustrates it. So we can start with a function x, then a particular function g can act upon the inputs x to make an output g of x, and then if g of x itself were then acted upon by another function f, we then have f of the g of x before it. So to go from this domain here, from this x all the way to f of g of x, that's called fg. So this is the composition. So the composition, this g of x essentially is the first step, and the final step in the transformation is we take f of the g of x instead of just f of simply the x. And if you look here, we actually work from back to front. So f g of x doesn't mean we perform f first and then g upon the input. As you can see here, we perform g first and then f. So fg means actually g's been performed first and then f secondly upon that. So let's try that with a few worked examples now where we're going to compose two or more functions together. So a, b, c, d and e, where h of x, k of x are defined as follows. So let's find first of all for a, h, k of x. But just before we begin, let's have a look at how these functions are defined. They're defined on a standard input, just a singular x. So the standard input here for h, if it were just a standard x, the function h takes the input, the x triples it, and then subtracts 2. For k takes the input, which is x, squares the input, and then subtracts 1. And so if I just underline here what h of x is actually doing, h of x is the same as tripling the input, then minusing 2. And then in blue, k of x, just to remind ourselves, is different. K of x takes its input, squares it, then subtracts 1. So here, hk of x means we're doing h of the input, not of x itself, but this time k of x, so the input is a function in its own right. So let's just be thinking, what does h do as it's defined above? So h takes the input, triples it, so normally it's 3 x's, this time it's going to be 3 lots of k of x, because that's our new input, then minus 2. So that's because, of course, the input here is k of x, and k of x, we're going to define in a minute algebraically. So going back to the definition of what k of x does, but keeping it within what we're doing here, k of x is x squared minus 1. So we just infill this instead of what k of x is here. So instead of the notation for k of x, here's what it is algebraically. Just making that substitution in now, and all minus 2. So it's still h of x. It's still 3 times the input, where this is the input k of x, then minus 2 away. So finally, just need to expand this out. So we have 3x squared. 3 times minus 1 is minus 3, then minus another 2, gives us 3x squared minus 5. Next, let's consider k h of x. So this time, we're doing k of the function h of x. So this time, of course, h of x is 3 lots of x minus 2. So what does k do? Well, k takes the input, squares it, then minuses 1. So that's going to be h of x all squared, subtract 1. H of x, we can infill what this is now. So h of x is 3x minus 2. So that just means 3x minus 2 all squared minus 1. So again, the input here is not just x, it's h of x. So h does 3 lots of the input. So k takes the input, squares it, and subtracts 1. So if we just expand these brackets and simplify, 3x all squared gives 9x squared. We take the product and double, that gives minus 12x's. Minus 2 squared is positive 4, then still minus 1 at the end. Simplifies down to 9x squared minus 12x, and 4 take 1 is positive 3. Now, h of hx, that means h is going to be applied twice. Now, a different way h of h could be written is h squared of x. In the same way, k squared is the same as k of x. So this doesn't actually mean we're doing h of x then squaring it. H squared is just notation for meaning we're applying the function h twice. So what is h of x going to be? Well, h takes something, triples it, then minuses 2. So h of x is going to be, I keep putting it down a h, it's going to be 3 lots of the input, which is going to be itself, h of x minus 2. So h of x is that so far. Then we just infill algebraically what h of x actually is. So h of x is 3x minus 2, and all that, of course, subtract 2. Then expand. We have 3 times 3x, which is 9x, 3 times minus 2, which is minus 6, then minus another 2, which simplifies to 9x minus 8. Next, hk of 3. So this time, we're going to h of what k of 3 is. So that means h takes the input, triples it, then minuses 2. So h of k of 3, we can work out what k of 3 is first of all, actually. That might be a slightly easier way of doing it. So, if you've actually got an actual input to use, what I'm going to suggest we do is just work out k of 3. So k of 3 is just simply 3 squared minus 1, which of course is 8. So h of k of 3 means the same as h of 8, because we just obviously evaluated what k of 3 is, which is 8. So h of 8 means 3 lots of 8 minus 2. 3 times 8 is 24, minus 2 is 22. And finally, k squared of 2, that's the same as saying k of 2. So k of 2, kx is x squared minus 1, so k2 will be 2 squared minus 1. 2 squared is 4, minus 1 is 3. So in other words, therefore, k of 2 is going to be k of 3, because we just worked out that, sorry, k of 2. K of 2 is 3. So now we just input 3 instead of 2, what we just did. So k of 3 is just going to be 3 squared minus 1, which gives 8. Now let's have a look at a second worked example, a slightly different one. This time have a function f defined as follows. This is called being defined piecemeal, so it's being defined in 2 different pieces. So if x is less than 2, the function gives x minus 2 all squared plus 1. But where x becomes 2 or greater, the graph becomes 3 lots of x minus 5. So first of all, we're charged with the idea of sketching this graph y equals f of x. So let's get some axes ready to go, and then we can actually have a go at plotting it. So here's one I made earlier. So let's just think about the crucial point where x would be 2. So this one here, I know obviously it can't actually be 2, but if x were 2, what we'd have here would be 2 minus 2 all squared plus 1, which would be 0 squared plus 1, which is 1. And so this graph obviously can't attain a value of 1. So it's going to be going close to a value of f of x being 1, but because x has to be less than 2, it'll never actually get quite low down enough to be 1. This here, when we square it, will be something negative actually squared plus 1, which will come out to be more than 1. The turning point here would be 2, 1, because this is in completed square form. So the lowest it would be going would be at 1, where x is 2. But of course, because this one here is x less than 2, we can't actually quite have that, so we fill in a hollow circle. If x were equal to 0, the intercept of the y-axis would be 0 minus 2 all squared, which is 4 plus 1, so it's going to cross the y-axis at 5. And as I said, it's going to be parabolic. That would have been its minimum point if we were allowed to plot it. So it's going to be something like this. It's not quite gone through 5, but anyway. This time, if x were 2, we'd have 3 lots of 2 minus 5. 3 times 2, of course, is 6. 6 minus 5 is 1. So this one actually is allowed to be 1. So this one would have a gradient of 3, and when x is 2, y is 1. So actually we can have this one. So the point 2, 1 is essentially included, and the y-axis intercept for this would be minus 5, because this is the plus c, going back to y equals mx plus c form. So if I just draw this in now, so it's going to be like that, and that's going to be down at minus 5. So for part B, it says find the value of f(0). So f of 0 means f of whatever f of 0 actually is. So f of 0, when x is 0, we're obviously looking at the blue portion of it, because when x is 2, it's defined upon this. So f of 0 is obviously 5, because when x is 0, this one gives a value of 5. As we can see here, when x is 0, it's 5 high. So that's essentially just f of 5. And so if we do the f of 5, when x is 5, we're actually on this part of the function now, because x is greater than 2. So now we're going to take 3 lots of 5 minus 5. So that's going to be 3 times 5 minus 5, which gives 10. So f of 0 is 10. Finally, C, it says find the range of values of x for which f of x is greater than 17. This time, I want us to imagine where the graph is at a height of 17. So where is y 17? So obviously this isn't to scale by any stretch. But if imagine this was the line y equals 17, we can visualize what values of x we're looking for. So we're looking for anything where x is greater than this value here. If x is to the right hand side, then f of x in red is obviously greater than 17. So we're looking at, essentially we're wanting this area here, so anything to the left of this one. So that's one of the functions, so one of the roots we're looking for, that one. And over here, where the y equals 17 line crosses the curve of the blue one, I'm looking for this one here too. So this one here is the solution where f of x is greater than 17 when this curve is obviously higher than this green line, which is anywhere here and upwards, and this one's going to the left over here, so we're wanting x this, or being less than that. So essentially we solved 2 halves. It could be that the blue bit here equals 17, so let's solve this first. I'm going to split into 2 halves, because you're going to have 2 solutions, one here and one over there. So first of all, when does the blue equal 17? So first of all, I'm solving x minus 2 all squared plus 1. When does that equal 17? So if I subtract 1 from both sides, I'm wanting x minus 2 all squared to equal 16. If I square root this now, I get x minus 2 equals square root of 16 plus or minus. Obviously consider both plus or minus. However, if I'm looking at this blue region here, I'm actually only concerned when x is going to be less than 2. So the positive root here I want to reject, because plus 4 would be taking us into this red bit of the function. The blue is only defined as 2 or less, so therefore we're wanting x minus 2 to equal negative 4. So if x minus 2 equals negative 4, therefore x equals minus 4 plus 2, which is minus 2. So x equals minus 2 is going to be our first solution. So minus 2 or less. And for the second bit, I'm trying to solve, in fact here, because it's actually an inequality, isn't it? So here I'm wanting x to be less than negative 2. So just to make that little correction here. Then solving for the red is 3x minus 5. So I want to consider where 3x minus 5 is going to be greater than 17. This time we'll start with the inequality symbol, so I don't have to remember that it's an inequality to begin with, as I almost forgot here, which was rather silly. So 3x minus 5 needs to be greater than 17. This is a much more simple rearrangement. Add 5 to both sides. I get that 3x has to be 22 or greater, so therefore x needs to be at least 22 over 3. So we can put these 2 bits together, these 2 solutions. So therefore what we're wanting is x less than minus 2 or x greater than 22 over 3, like so. And that completes the solution. Now, it's probably a good idea for you to try some of these independently, just to build on your fluency with how to compose compound functions. So here's an activity which we've put together for you. So there's 6 different composites here to try, and there's 4 different functions here which the composites are going to be defined upon. So f of x is x squared plus 1, g of x is x plus 3, h of x is 2x minus 1, and k of x is x squared minus 3. And so you're given what these composites actually should equal. It's your job to actually compute these manually and show that each one is indeed what it says it is. So treat each of these as 6 show that type exam questions for practice. Press pause now and try them on your own, and then press play and see how I'd probably do it myself, but hopefully, having seen these solutions, you should be more or less okay with a bit of patience. Okay, so assuming you've had a go yourself, here's how I would have probably tackled it myself. So first of all, I always think about f of x, g of x, and all these in terms of the input x. So if I just highlight the x's here first of all, f of x takes the input, squares it, plus 1. G of x takes the input, adds 3. H of x doubles the input, takes 1. K of x takes the input, squares, minus 3. And I've underlined here what the actual functions are. So first of all, k of g of x, I did this as follows. G of k of x, I would derive in this way. F of g of x, like so. H of g of x, 2x plus 5. H squared of x, which means h of x, not literally 2x minus 1 all squared. So this would be h of x, which is h of 2x minus 1. So 2 lots of 2x minus 1, 4x minus 2 minus 1, which gives 4x minus 3. And finally, g squared of x, which means g of x, would go something as follows. So hopefully now you're a bit more confident with how to knit these together and how to work backwards, back to front almost. So let's have a look at a final worked example where we're going to have a look at a logarithmic one. So exponential and logarithmic functions and composites. So we've got 2 functions here. P of x, which is ln of x minus 3, where x is any real number, but x must be greater than 3 itself. And q of x, which is e to the power of 2x plus 1, where x is anything real. So find the function qp of x, stating its domain and range. So this one here, even though it doesn't say, I might well just sketch a graph of it. So qp of x means we're doing q of whatever p of x actually is. So q of x takes the input, does e to the power 2 lots of it, then adds 1. So this time, because our input is p of x, what that means is q of p of x is going to be e to the power of 2 lots of p of x plus 1. So how is p of x actually defined? Well, p of x is defined as ln x minus 3. So if I just sub in what p of x actually is, p of x is ln x minus 3. That means I've got e to the 2 lots of ln x minus 3, then plus 1. So this means e to the power ln x minus 3 squared plus 1. But e and the ln are inverses of each other. So e to the power ln essentially undoes each other. And so this is just going to leave us with x minus 3 all squared. Of course, then plus 1. X minus 3 squared, expanded out. Even though this is nice because it's in completed square form, actually. So that would be x squared minus 6x plus 9 plus 1, which goes to x squared minus 6x plus 10. And so actually, although this is a fully expanded and simplified version of what qp of x is, then this one here is nice because it's also in completed square form. So actually I would accept both this one and also this final one as valid expressions for what qp of x actually is. So this here, because it's in completed square form, this tells us the turning point. So the turning point would be when x is 3, y is 1. But of course here x has to be greater than 3. And so because we're doing e to the power of something natural log, we actually get just a parabola back from this because e and the ln, as I say, undo each other. So if I imagine this as a graph, this will just help us think about the domain and range next. If x were allowed to be 3, y would be 1. So if I imagine it were 3 and were 1, it would start here. But of course, we're not actually allowed to be at 3, so that's going to be a hollow circle. But after that, it will be this parabola. But because we're only looking at the bigger side of the turning point, it's just going to be half of a parabola, essentially. So q, p of x, this whole thing here, will look like this. And so we can now think about what the domain and range is. So the domain is restricted from the off because the domain of p was restricted to x being greater than 3, and so that also feeds into the restriction on q as well. If x is only 3 or greater going in, it means that we can only have x being 3 or greater, assuming it makes no problem for q, which it doesn't. So the domain is, again, x needs to be greater than 3, and the range of what qp of x can be, qp of x, of course, the lowest it could have been would be at height of 1 when x is 3, but because x is excluded from being 3, actually the curve is always going to be greater than 1. So the range is qp of x greater than 1. So that's also that part done. So the function qp of x is this, and its domain and range are here. So now over to you to try some bookwork on your own. So exercise 2c, starting at page 34 rather to 35. Damn, silly me. We'll give you some good practice. So that should say page 35. Have a go. Questions 3 to question 11 would be my suggestion. Try as many as you can, including the extension, of course. The more, the better. So keep plugging away. Attend revision sessions if you can. Ask for help if not. And never, ever give up. Until next time, it's goodbye from me.